In this video, we're going to solve the equivalent resistance at the terminals A and B for this particular circuit. Now, this is one of the hardest examples we have seen, and it's not necessarily hard. I would say the circuit is just, it seems more complex. But as you go step by step, you will see this circuit problem is not hard at all. Alright, let's begin. So we know we're going to be looking in through the terminals A and B, which is going to be this way. And they want us to find out the equivalent resistance, right? Now, when we look at this, we know this is going to be the terminals. And we normally start at the branch furthest away from these terminals. So we're going to start on this side of the circuit, right? Now, when we look at this side of the circuit, I want us to notice something. We have a resistor here, and in this branch, we don't have any resistor here. So you have two options, right? The first option is you can look at this and say, well, if there isn't any resistor here, that means that no current is going to flow in this resistor because current is always going to take the path of least resistance. So when the current leaves this resistor and it goes this way, once it reaches this node here, it has two options. But because there is no resistor here, we know that no current is going to flow this way. Therefore, all the current is going to flow this way, which means this resistor is basically useless to us. So we can kind of just discard it for now. That's one way to look at this problem, right? If you cannot see that, another way you can tackle these problems is to remember, if you have a particular situation where you have a branch that does not have a resistor, you can always add in a resistor, right? So for me, I'm just going to add in a resistor right here at this branch. That's all I'm going to do. Alright, so I'm just going to redraw this circuit diagram. And when I redraw this circuit diagram, I'm going to add a resistor in this branch. And the value of that resistor is going to be 0 ohm. So let's redraw this. Now we all should at least been able to draw the first loop. We know this resistor is going to be 50 ohm. I'm just going to label 50. This one is 25. This one is 24, and the value of this resistor is 10. Now let's move to the second loop. As we can see, we have this diagonal line here. So I'm just going to treat it as a vertical line because I know it's going to be in parallel. So I'm just going to draw it as a vertical line that looks similar to this. And that's going to be 40 ohm. And we know we have a wire with a 20 ohm resistor down here. So I'm just going to draw that. We have 20 ohm. Let's continue. We have this wire with a 28 ohm resistor. And then a 16 ohm resistor. That's 28, 16. Then we have a 30 ohm resistor, a 60 ohm resistor, a 18 ohm resistor, and finally, and one of the most important pieces is to draw in this resistor here and label it 0 ohm. Alright, we know this is A, this is B. So we're going to start right here, right? When we look at these two resistors, are these resistors in series or are they in parallel? Well, we know these two resistors are going to be in parallel, right? So because these two resistors are in parallel, let's find the equivalent resistance. We can say 60 multiplied by 0 over 60 plus 0. That's going to give you 0 ohm. Therefore, we know the equivalent resistance of these two resistors that are in parallel is going to be 0 ohm. Let's just redraw this circuit diagram over and put that in place. And we know this resistor here is going to be the equivalent resistance of these two resistors, which was 0 ohm. So once again, if you were able to look at this circuit and intuitively understand what is happening, you know that current will always flow through the path of least resistance. Therefore, when the current enters this node, because there is no resistor in this branch, the current will not flow through this resistor at all. The current is just going to flow through this branch, thus eliminating this 60 ohm resistor to begin with. Now, if you cannot really see that, anywhere you have a branch with no resistors, you can always add a resistor and label it as 0 ohm. And then you can use the knowledge about series and parallel resistors to find the equivalent resistance. Alright, let's continue. So now when we look at this, we have this 30 ohm, 0 ohm, and 18 ohm resistor, and all of them seem to be in series. Once we identify these resistors are in series, we're just going to add. We have 30 plus 0 plus 18. That's going to give us 48 ohm. So let's redraw the circuit diagram once again. And we know this resistor right here is going to be 48 ohm. So now that we have this, we can continue to simplify this circuit, right? It's not hard, but you must be able to identify which resistors are in series and which resistors are in parallel. So when we look at this, we have these two resistors here. Are these in series or are these in parallel? Well, we know these two resistors are actually going to be in parallel. Why? Because when the current enters this node here, it's going to split. It's going to go this way and that way. So we know these two are in parallel. So let's find the equivalent resistance for these two resistors that are in parallel. We can say 48 over 16 divided by 48 plus 16. When you solve for that, that's going to give you 12 ohm. So now let's redraw this circuit diagram now that we have found the equivalent resistance for these two resistors. And we know this resistor right here is going to be these two resistors that are in parallel, and that's going to, we know this resistor here is the equivalent resistance of these two resistors that are in parallel, and that's going to give us 12 ohm. So we have 12 ohm here. Now let's simplify this further. We know these two resistors are in series, so we can say 28 plus 12, that's going to give us 40 ohm. So we just found the equivalent resistance for these two resistors. Let's redraw this once again. Yes, I know, it's a lot of redrawing, but that's how we're able to solve these problems, right? Especially as engineers, we need to have diagrams, and sometimes we just have to keep drawing until we have what we're looking for. And we know this resistance right here is going to be this 40 ohm resistor, which is these two resistors in series. All right, now when we look at this, we have these two resistors and they're actually going to be in parallel, right? So we have 40 times 40 over 40 plus 40. That's going to give us 20 ohm. All right, so let's redraw this circuit again. And we know these two resistors are going to give us 20 ohm. So we can just draw that right here. Now when we look at this, we have these two resistors that are in series. So we can say 20 plus 20. That's going to give us 40 ohm. So let's now redraw the circuit representing these equivalent resistance. We're almost there. I know this one is a long problem. We're almost there though. So let's redraw it. Now when I look at this, I have 40 ohm, right? We know these two resistors are going to be in parallel, right? So because we know these two resistors are in parallel, let's solve for that. We have 24 times 40 equals 24 plus 40. That's going to give us 15 ohm. So let's redraw this circuit. This is 50 ohm, 25 ohm. This right here is going to be 15 ohm. And this resistor is 10 ohm. Now let's look at this again. Let's analyze what we have, right? We know a current is going to be coming out of this terminal, terminal A. And it's going to go this way. And once it reaches this node here, it has two options. It can go this way or it can go this way. And because we know that these three resistors are going to have the same current flowing through it, which means that these two resistors are going to be in series. So we can say 25 plus 15 plus 10, that's going to give us 50 ohm. So let's redraw this circuit again to represent the equivalent resistance for these three resistors. So we have something that's going to look like this. We know this is 50 ohm. And the equivalent resistance for these three resistors is also 50 ohm. So we have 50 ohm. Now when we look at this, we know these two resistors are actually going to be in parallel, right? So because these two resistors are in parallel, when we solve for this now, the equivalent resistance for these two resistors is just going to be 25 ohm. So let's draw this circuit one more time to represent the equivalent resistance looking from terminals A and B. We know that this resistance is going to be 25 ohm. Therefore, you can say the equivalent resistance at terminals A and B is going to be 25 ohm. So this is going to be our answer for this problem, right? This was a very, very long problem, but not necessarily. It was just a lot of steps that were involved, and you had to be able to understand series and parallel resistance in order to solve this problem. So I think if you were able to solve this problem, you can solve any problem that you might see when it comes to series and parallel resistance. When it comes to finding the equivalent resistance